Okay, so let's just think about, because we know how to do this in one dimension, so let's just think about the things we have to worry about in one dimension so that we know what the analogs are, at least of that in higher dimensions, so we know what we need to worry about. So let's take this example. And you know that if you want to try to do this integral by hand, you're going to want to make some kind of substitution for x squared. So you might propose a substitution, let me call it g of x. The new variables will be called u, and of course x squared is the obvious substitution to do here. Okay, then what are the things that we have to worry about? Okay, okay. You know, hopefully substituting in for this function isn't too hard here. The things that we have to worry about are, well, what happens to the dx? Okay, so what are we thinking about here? What we're really thinking about is that, you know, we've got some domain. This is our x domain from 0 to 1. And then we decided to do a change of variables onto our u domain. Right, and we have these little differentials here, which you can think about when we break this down from the definition of the Riemann integral. What are we doing? We're looking at the value of the function somewhere in a partition times the base width. So what we're really asking is what happens to these base widths, right? The function values, the function should still take the same values at different locations maybe, but what is happening to the width of these rectangles? Okay, so I might have a little base here, but it might not stay the same size. It might change. This transformation might change the area of these things. And, you know, this one over here, maybe this one will get smaller. Maybe some will get bigger. You know, so we have to worry about this. What happens to these little areas, little volumes? And then the other obvious thing that we have to worry about is what happens to our limits. Okay, in one dimension, this is not such a hard thing to worry about. You know, we start with an interval. As long as we have a nice mapping, a nice change of variables, we end up with another interval. And it's easy to decide what our new limits are going to be. Of course, in higher dimensions, things get more complicated, right? In higher dimensions, we may start with a region, and then we map to some different region. And things get more complicated here because we know that it's not possible to integrate over all possible regions. We could have pathological domains where the integral just is not defined, right? The upper sums and the lower sums just do wildly different things. So this is something that we should worry about here. Okay, great. I started with a nice set that I can integrate over. Did my change of variables do something pathological that caused this to be something that I don't know how to integrate over anymore? Okay, so this is going to be really the question that we're worried about, not what is the new shape of this thing. Whatever the new shape is, we can write down the definition of the integral. The question is that well-defined? And what we're asking is this going to give us a well-defined integral? as long as we start with a sufficiently nice set. So if G is regular on a compact Jordan measurable set, okay, then we're in business. G of S, so the image set, which is going to be our new domain of integration, is also compact. Okay, bounded is good. We can't do Riemann integrals on unbounded sets, so bounded is good. It's compact and Jordan measurable. So this answers the question of what do we do with the limits, okay? You know, of course, particular examples, there are details. You have to work out what happens to the limits. One can do that. But one doesn't have to worry that we're going to create some kind of monster that's suddenly not integrable. And that's the real concern. So limits are not a problem. Then what was the other issue? The other issue is what happens to the dx. And that, we said, is really a question of what does my transformation do to areas or to volumes, right? Does it take this little, in 1D, this little base of my rectangle? Does it take it and keep it the same? Does it stretch it a bit? By how much does it stretch it? Or does it compress it? That's what we have to figure out. How do volumes change under this transformation? Okay, so our question 2. How do volumes change? Under nice transformations. Okay, so we're going to spend a lot of our time on this, thinking about the easiest transformations we can imagine, which are linear transformations. That's not a big limitation for us, because we're already assuming that we're working with nice transformations, differentiable transformations. We know that differentiable transformations locally look like their linearization. Okay, so if we can understand linear transformations really well, then hopefully it's not a big step to then non-linearize things. So let's start easy. We'll start as easy as we can, and build up until we're ready to put together fully nonlinear things, which will probably be on Thursday. Okay, so let us start with linear transformations. All right, my starting place is going to be linear transformations on rectangles. In fact, I'm going to start with easy linear transformations on rectangles. And we'll build things up to more complicated things as we go. All right, so first of all, rectangles. Okay, so R is just some rectangle in Rn. All right, and our transformation is of the form A times X, where A is some matrix, an invertible matrix, right? We know we only want invertible matrices. All right, now I'm not even going to do every possible matrix here to start with. Eventually we'll get to every possible invertible matrix. I'm going to start real easy. I'm going to start with basically the identity matrix, and I'm going to do really simple things to the identity matrix and see what happens. These are called our elementary matrices, where you take the identity matrix and you start performing elementary row operations on it, just one at a time. So let's start with, obviously doing this for the identity matrix is not interesting. The identity matrix leaves everything put and volumes don't change. So we got to go a little more complicated than that. But we're going to go the least a bit more complicated than that than we can. So let's start with elementary matrices. Right, so A is obtained by performing an elementary row operation, a single elementary row operation to the identity. All right, there's basically three things that we can do, if you remember, in elementary row operations, like when you're row reducing your matrices. There's not that many different things you can do. What are the elementary row operations? Yeah?
Just scaling.
Rescaling, okay. All right, that's a good one to start with. Let's multiply a single row, row I, by some constant. Okay, so what is this going to do? I start with a set, right? So AX, matrix vector multiplication. And what does this do? Remember, A started from the identity matrix, right? This is a diagonal matrix still. And what are we going to get? We're going to get, essentially just the ith row of X. So the ith component of this, let's say this, or the jth component of this, is going to be really just the jth component of X, right? It just the identity multiply acting on this. And the only exception is in row I, we're going to multiply by C. Okay, so we took a rectangle. And most of the dimensions, this thing stayed the same. Along one of the dimensions, everything got multiplied by C. So now all of a sudden we're going to have maybe A2 and B2 stay the same. But now this is going to be CA1 and CB1. Okay, so how does the volume of my transformation, if this is R and this is L of R, how do these volumes compare? What happened to the volume? It just got multiplied by C, right? Most of the dimensions, everything stays the same. One of the dimensions, things get stretched by a factor of C, so that comes up in our volume computation. All right, and this information, this scaling factor is encoded in the matrix. It's encoded in the determinant of the matrix, actually, right? The determinant of the identity matrix was I. Now, we've changed one of those to C. The determinant became C. Okay, so that's one elementary row operation. What are the other ones? Yeah.
Switch the orders around.
Okay, we'll swap two rows, sure. So let's swap rows I and J. What does that do to the volume of our rectangle? Nothing, yeah. All we've done is taken it and kind of reoriented it. We haven't changed the volume at all. So doing this does nothing. And what's the volume of my, what's the determinant of my matrix in this case? Almost? -1, yeah. So it's not quite true that this is just the determinant of A times, so this should be times the volume of the rectangle. That's not quite true, it's just the determinant of A, but it's at least the magnitude of the determinant of A, I guess, times the rectangle. That's really true here too, because C could be negative. So probably we should have done that. All right, last one. So what's our last one? We have to take one of the rows and add some multiple of another row to it. That's our last possible elementary row operation. Okay, so let's add C times row I to row J. Okay, so again, let's do this one explicitly. Again, most of these things, nothing is going to happen, right? We've only changed the action on one row. Otherwise, this thing is the identity matrix. Okay, so in most places, nothing is going to happen here. Okay, the only place that we're going to change things is right here, row J. And what are we going to do? We're going to start with xj, and then we're going to add C times xi. All right, well, what does that do to volumes? This one is maybe not quite as obvious to look at what's going on here. So let's try it and think about it. So let's say we started with my A1, B1 here, A2, B2. Okay, so along most of the dimensions, nothing at all is changing. Okay, so maybe this dimension is where things are going to change. Everything else stays the same, so we're still going to be stuck between A2 and B2 everywhere. All right, now I come to here. Now previously I was at A1. Now I'm going to add C times A2 to that. Okay, so my base is going to shift a little bit. And that's going to be true all the way along here when I get to this point. Instead of keeping B1 put, I'll take B1, but I'll add a little bit to it. Now there are other points in my rectangle. Okay, so my other points in my rectangle as I come up here, so this should actually be up here though. The y coordinates don't change. What about this corner? Well, this corner, I had an A1, B2. The B2 part is going to stay the same. Now I'm going to take A1 and I'm going to add C times something, right? So what am I supposed to add? C times this component. So C times B2 this time. All right, so this is going to get shifted a little bit more. All right, I'm essentially taking my x component and I'm adding C times my y component. So the fact that my y component means bigger means I get a bigger shift. Same deal over here. I'm going to take my original location, B1, and I'm going to add C times B2. So I'm going to get a shift over here. And at all the in-between points on my rectangle, the same thing is going to happen. The amount of the shift changes depending on how high I am. And I'm going to get this parallelogram coming out. Okay, so this becomes my L of R. All right, we could ask ourselves what's the volume of this, or maybe you can see it. If not, we can set this volume calculation up as an iterated integral, for example. We have the technology now to do that. So what is this? This is going to be integrating over our dimensions. Well, AN, BN, down to A2 to B2, assuming that the changes happening in the first dimension. Okay, and now here we're integrating from a1 plus cxj to b1 plus cxj. Okay, so our limits have changed a bit. Right, and our limits along here depend certainly on where we are vertically, on the jth component. All right, and then we have this iterated integral. But what happens when I do this inner integral? I do this inner integral, and actually the xj's cancel out, right? I get b1 plus this minus a1 plus this. All of a sudden it's just b1 minus a1 again, which is just the original length along that dimension. Nothing has changed. And then, okay, b2 times b2 minus a2 all the way down. So actually the volume hasn't changed at all by doing this. I've just kind of picked up these points and maybe shifted them. They fill here and I get my original rectangle back. So this is actually still the same as my original rectangle. And what happens to the determinant when I do this elementary row operation? Well, remember, it's not so hard to work out because we actually started with the identity matrix. So we started with the identity matrix, so we had 1s on the diagonal and 0s everywhere else. Then pick a row. To one of these rows, I added c times something else. So one of these zeros gets changed to a c. Everything else stays the same. Let's just pick that one. Everything else stays 0. Okay, so what do I have? 1's on the diagonal. One other element is a c. Everything else is a 0. What is the determinant of this? It's still 1. Okay, so once again, this is the determinant of A times V of R.